I'm Rusty Holden. I'm the manager of Thorium LLC. My firm has sponsored computational studies that have been performed at PNNL. I'll briefly go over some insights and some interesting results. Let's start with the idea that thorium is indispensable for shifting the nuclear energy paradigm to a new one that is sustainable and renewable. It's a little rubric to get us in the mainstream, okay? Without thorium, this paradigm shift is impossible. As we heard yesterday, thorium avoids the transuranic burden associated with the captured products of uranium-238. Thorium generates uranium-233, an excellent fissile material during reactor operations. Fission products can be removed from liquid or metallic thorium fuels with relative ease. Let me present ideas about bringing thorium into the mainstream. The applications for thorium to move it forward include weapons-grade plutonium disposition, spent fuel transuranic disposition, modular reactor for distributed process heat supply, and finally large-scale electric power generations from, I think, clusters of low-cost, factory-built modular reactors. To improve thorium's prospects for widespread commercialization, Thorenco has looked at metallic fuels. These special application fuels provide a way to destroy plutonium from obsolete weapons and to better manage accumulated transuranics from spent fuel. Hundreds of computational simulations were conducted at the Pacific Northwest National Laboratory by my friend Richard Whitman. The best reports were generated a report that was reviewed by Dave Wooten, a skilled computationalist, and the head of nuclear up there, a fellow by the name of Jim Bell. The reasons we studied the metallic thorium include longer burn times. I cut the machine off at 120 months. That was plenty long for a stable run. With metallics, you have the option for hydrogen doping of the fuel, for temperature, for enhancing temperature influence feedback effects. You have fuel stability. Of course, we produce the uranium-233. The advantage, I think, is the production of uranium-232 for proliferation hardening purposes. The metal fuel has superior heat conduction, superior proliferation resistance, and the final key, it has the attribute of recyclability, I call it, via zone refinery. In any system that uses nuclear fission, the fission products will be generated. These remnants have half-lives, for the most part, of 30 years or less. Zone refining provides a way for the fission products to be removed from the metallic fuel, avoiding wet chemistry systems. Wet chemistry generates solid and liquid waste streams that have significant volumes. A little detail I learned up at Hanford. They're still working on it after 40 years, I think. In contrast to zone refining, an induction coil heats a thin slice of used metallic fuel rod in a quartz boat and melts that slice, starting at one end. As the boat carries the used rod through the induction coil slowly, the melt travels the length of the rod, taking along with it the lower melting point impurities. Many of the lower melting point fission products are collected in the melt at the other end of the rod, and the rest of the fuel alloy is ready for refurbishment and reuse. The fission product residue can be concentrated, collected, and placed in storage for the 300 or so years it takes most of them to become stable. The longer life fission products can be irradiated to make them stable. PNL's computational simulations developed reactor geometries and materials for thorium converter reactors that use metallic thorium. The converter reactor is one with the mass of the fissile uranium-233 produced. It matches the mass of the fissile uranium or fissile plutonium that is fissioned during operations. By definition, converter reactors are renewable because they grow new fuel in the amount they burn while they generate merchantable heat. Plutonium thorium fuels are for use in secure government facilities, and uranium thorium fuels are for use at municipal or industrial facilities. Results show that weapons-grade plutonium and reactor-grade plutonium with associated transuranics can be fissioned away safely. We found that civilian nuclear waste and surplus military plutonium can generate copious quantities of electricity and plenty of uranium-233 safely in secure, fast, lead-detected cooled converter reactors. Once the transuranic fissile isotopes are fissioned away, they cease to exist, resolving risks and ending costly stewardship issues. Destruction of these isotopes is a better treatment solution than guarding and storing the explosives for geologic ages. Thorium advances disarmament and non-proliferation objectives when thorium is used as the fertile component of plutonium-containing fuels. Another system is efficient as a thorium system for burning out and transmuting the usual suspects from the first nuclear age. The usual suspects being neptunium, plutonium, americium, and the curium isotopes. For worldwide industrial applications, we found that thorium-uranium converter reactors exhibit renewable energy attributes. New fuel is grown in the reactor as the load of starter fuel is consumed. The amount of new fuel equals what has been consumed. The process is sustainable as well because the fission products can be economically stripped out of the fuel, allowing fuel to be used over and over again. Transuranics are not produced in as significant a quantity, and the fuel matrix alloy is amenable, again, as I said, to the zone refining process. Now to the specifics. We put together 3 converter reactor configurations to burn thorium metallic fuels. One is something I call the Plutonium Eater, which gets rid of the weapons grade to advance the disarmament objective. It supplies 400 megawatts of thermal power continuously for a decade. The next one is I call the multinational transuranic eater, which gets rid of the transuranics as a group, supplying 400 megawatts continuously for a decade. And the third one is the commercial converter reactor, which I call the producer, which is an encapsulated, transportable, factory-built reactor that supplies process heat in increments of 10 to 50 megawatts. The Plutonium Eater uses a lightly doped, that is hydrided metallic thorium plutonium fuel that is cooled by lithium 7 lead eutectic. This reactor produces, as I told you, 400 megawatts of thermal power continuously. It burns out about 1/2 the plutonium-239 in the fuel, that is a ton or so, and produces a ton of uranium-233 during its decade of operations. The thorium load in the device is around 20 tons, some in the fuel and the rest elsewhere. The simulations revealed that the lightly doped hydride fuel was reasonably stable for a decade. This application brings thorium to the center of the world stage because it provides an effective method to transparently advance disarmament objectives now that there's a large surplus of military plutonium and that the Non-Proliferation Treaty is up for renegotiation on its 40th birthday. The transuranic eater is for spent fuel applications. The transuranic isotopes and the proportions found in spent fuel leaving the cooling ponds is alloyed with metallic thorium. The fuel is doped lightly with deuterium and hydrogen in this case, a little differently than the plutonium eater. This reactor uses a hotter neutron spectrum and uses metallic lead as its coolant. It burns out neptunium and plutonium isotopes and transmutes americium and curium. Like the plutonium eater, this one burns out a ton of plutonium and produces a ton of uranium-233 during a decade of operations at 400 megawatts thermal. My favorite is the producer. This is an industrial reactor that I think it could be made into a smart reactor. It's factory built, transportable, and has flexible applications. It supplies 10 to 50 megawatts thermal At a power of 10 megawatts, the fuel lasts for a decade. At 50, it lasts for 5 years. The metal fuel is designed to be highly deuterated so that the rate of neutron multiplication is greatly influenced by fuel temperature. As things get hot, the population of thermalized neutrons declines because moderator density is reduced. The fuel is, in this case, is doped with deuterium heavily. The in-fuel neutron spectrum is tailored by the doping so that the spectrum is best for neutron capture by thorium. The producer core can be designed to be subcritical at high temperature and slightly supercritical in the temperature range of intended operations. The coolant in the neutron active area of the core is lead bismuth eutectic or lead lithium 7 eutectic that convects without the need for mechanical pumps. Heat is extracted from the nested vats of liquid metal with a power loop of supercritical carbon dioxide. The reactor is factory built and transportable on water. The core is encapsulated by solid lead alloy during transport and liquid lead during operations. Fuel is only removed in the factory environment. The producer can use floating platforms to provide electricity and process heat for desalinization to major port cities around the world. The core is small and nothing is complicated, as I said, and a set of nested vats of liquid metal. The cladding is EPA-23. That's the Russian stainless that was used in their program, a submarine program, and its counterpart here in the United States is HT9. This steel can be used throughout the system. It looks like the stability is maintained for the decade of operations, which I think is fairly good considering the simplicity of the device. Plus, pressure vessels are not needed. There's no high pressure region in this converter reactor because water has been excluded from the design. Moderation as needed is provided by the hydrogen doping of the fuel. Lead and its eutectics are used because they're not chemically reactive in contrast to sodium and potassium. Costs are reduced for the industrial reactor because massive containment architecture is not needed. The volume of liquid metal in the vats is large compared to the core, giving the industrial system a thermal inertia that buys plenty of time for conventional control features to manage any overheating scenario. Lead alloys allow the neutron spectrum to be shaped for the application. Less fissile material is needed in the core as hydrogen is introduced to increase moderation. However, the thermal spectrum causes the useful life of the fuel loadings to fall off. We think because the fission products poison the chain in the thermal and a spectrum I call the super soft spectrum. The geometry is a little different than a conventional reactor. Plates are used in a cubic array. Things are developing fast on our thorium front. Los Alamos D Division is writing code for thorium applications presently. This will provide tools for the regulatory community. As we know, Senator Hatch and Senator Reed introduced Senate Bill 3060 on March 3rd of 2010. Perhaps by using planned concerted action, we can hector the energy committees with our thorium solutions. For weapons-grade disposition, the MOX program needs a backup because MOX generates plutonium from uranium-238 in the MOX fuel. MOX is the U.S. official program now for plutonium disposition, and I think it's deeply flawed. For the waste treatment applications and the power applications, thorium has a large place at the table. For Thorenco's work, the Los Alamos D Division has said preliminary computational fuel studies and plans and specifications for a pilot reactor can be generated in 3.5 years. D Division develops advanced computational software, has the skilled computationalists, and it has a superior library, and it has the Roadrunner, the world's, I don't know if it's still the world's fastest supercomputer, but the thing works pretty well, I've heard. I think the rapid computational path is the correct one for all of us. All of our machines and ideas that we have seen at our demonstration or our convention or our gathering can be modeled on the supercomputers to get very, very fast results and to weed out weaknesses immediately without much cost. I had plenty of bad ideas that I ran because I'm not trained in this field. I happen to be a lawyer. But it was absolutely fascinating learning how quickly we could get a printout or we could get a picture, a drawing from one of my first reactors. I decided it would be good to have an ellipse because I thought we'd have two foci there and we could control it with that. Oh, this would be great. So I had them rig it up, and sure enough, the neutrons behave like neutrons. They don't behave like what I thought they were going to do. They go everywhere. They do what they want. They don't care about foci. They're not going to be optically bound by anything. So once I got a little used to the way that the neutrons behave through this window, this computational window that allows us to see these very complex interactions over time, I was able to come up with these three prototypes in relatively short time using pretty much standard materials that are in the book, and with geometries that are sort of in the book and sort of new. And a lot of it was just working with the leads because I thought it was better than the sodium. I didn't want my thing to have all the problems Manju and Super Phoenix and the rest of them have. So you have the freedom, design freedom to come up with answers. So I think we can advance our cause very quickly now today because the computational results are considered scientific evidence. Many physicists believe the results, but the important thing is they can shape the experimental testing that needs to be done to get our fuel certified and our machines up and running. So I thank you, and if there are any questions, I'm here. I probably burned up all my time.
Oh, we got
You have a link to documentation?
Oh, hold on, buddy. Hold on.
You have a link to documentation?
I will supply some of the reports if you're, unfortunately, this thing, a lot of my work, because we make the uranium-233, we're governed by this thing called 10 CFR Part 810. And this CFR is the part of the local proliferation treaty regime.
I got it.
And because I make more uranium-233 than anybody else in the world, I'm very sensitive about what I send out because it's life in the can if I blow it. So I'll send you